All right, hello everyone.
Oh, sure.
Let's just wait another minute. We only have 8 people here, so just wait one more minute. Okay, let's get started. All right, so I went ahead and looked at our schedule to try and see where we are. You know, we have Thanksgiving holiday, which is going to mess us up, take another day from us. So I went through and I reordered everything. So this is not the same as what appears on this schedule. I redid it. So this is now going to be what we're going to try and cover. We only meet 8 more times, including today. So we meet 8 times and then we have a final exam. So there's only 8 more lectures left. As you can see here, I took out exam 3. So we are not going to do exam 3 in class in a Zoom session. Okay, exam 3 is going to be an at-home exam. Okay, that's what I put here. I'll send that exam to you on Tuesday after class. So immediately after I end the class on Tuesday, I will send out the exam. You'll have until Friday. So you'll have a couple of days to finish that and submit it to me by 9 a.m. on Friday. I'll give you a Dropbox link for that. Once I get the exams, I'll grade them that same day. And then I'll post the grades by 4 o'clock. And the reason I'm trying to rush that is because Friday the 13th, Friday the 13th is going to be the last day to drop a class. So I just want to make sure that everybody has an opportunity to see where they stand after 3 exams. So that's why I'm doing it that way. All right. Of course, the take-home exam or at-home exam will be, you know, I'm asking that you work alone, all that stuff, but I don't want you all to be forming study groups and stuff and getting on Zoom. But I can't really monitor that. So I'm just asking for you to do your own work, right? But these problems are going to be a lot of area volume problems, things like that. So they don't lend themselves to being able to look them up to get answers. You know, if it was just an integral, you could always just go look that up. But these, you have to translate the problem, you know, into a math problem. So that's why I'm giving it as a take home. I'm not so concerned about the academic integrity part of it. Okay, any questions about this?
Now, as far as the difficulty, is it going to be the same? Are we expecting to be a hard exam?
I think that what will be more challenging on it is that if you're trying to find like the area between 2 curves, or if you're trying to find the volume of something wrapped around an axis, the functions I give you may be a little more complicated, because I know that you're going to have access to graphing utilities. So I would expect that you can go onto Desmos or some website and graph things to help you, right? So that part of it would be perhaps more advanced than the basic functions that we've been doing here in class, like x squared plus 1, you know, like it might be something more advanced. And then I will also be asking you to completely evaluate the integrals. And what I mean by that is, remember I said I was going to have you just set up the integral and not calculate it?
Mm-hmm.
I'm going to have you set it up, but then I'm going to have you go to like Wolfram Alpha or something to calculate it. So to get me an answer, since you're going to be at home and using computer anyway, I'll ask you to, you don't have to show me all the work. You just have to go and, you know, do it on Wolfram or something.
Yeah, basically just prove the concept,
Yeah.
step by step, and then knowing whatever the units or the number that we're looking for.
Yeah, you have to get the integral correct, right? That's going to be the challenge for the test, is making sure that you get the integral correct. And once you get the integral correct, you can just go to a computer to get the answer.
Okay.
Okay, let's get down to business because we have a lot of business to do. So last class we were talking about sequences, and I finished up by talking about the limit of a sequence, and that when we take the limit of a sequence, we always let n go to infinity, and we try and figure out what's happening with the sequence and whether or not it's converging or diverging. So if the limit exists, we say it converges. If it doesn't exist, we say it diverges. So I thought what I would do to start is show you like a graphical representation of a sequence. And we talked about this last class. So let's say we take the sequence 1 over n. Okay, so this is actually the sequence a sub n equals 1 over n. So we know that, you know, first we plug in 1, we get 1, then we get a half, then we get a third, and we keep going forever. So what you can see here is a graphical representation of this sequence. And let me change something here. Let me change the y between 0 and 1. Let's do this between 0 and 30. There we go. Okay, so you can see here that when I start off, I plug in 1. I plug in 1, I get 1 up here. And then I plug in 2, I get 1/2 that's there. And then 1/3, 1/4, and then it keeps going. So it's like I said before last class, it's very much like the function 1 over x, except that it's not the curve, it's just a bunch of dots, right? So let's do something a little different. By the way, would this converge? Would this sequence converge? So how do we check? You know, does that converge?
I don't think so.
Take the limit, it then goes to infinity, right? That's what we do to see if a sequence converges. And then we do 1 over n, that's the sequence. So what would happen if I let n get big? This thing would head to
0.
Yeah.
So
So
it
does
converts.
this sequence converge? Yes, it does. It converges to 0. And you can see it with the picture that these dots are getting smaller and smaller, right? They're getting closer and closer to the x-axis. Okay.
I thought they would go to the x-axis, but then they will never like meet. They were just as if like it's a vertical asymptote.
Yeah, they won't ever get there, but is it getting closer to something is the question.
Yes.
Yes, it is getting closer to 0 without actually ever getting there, but it is getting closer to 0. Okay, let's do a different sequence here. How about let me just clear all this. Let's do a sub n equals n plus 1 over n plus 2. Let's just take a look at what that looks like, okay? I'm just trying to give you some visual, something visual to go off of here instead of just writing it down algebraically. So x plus 1 x plus 2. There we go. So there's the sequence, okay? Let me pull some of these points back. So when you plug in 1, okay, when you plug in 1, let's see, what would we get if we plug in 1? So what does this sequence look like? Plug in 1, we get 2/3. Plug in 2, we get 3/4, 4/5, 5/6, and that keeps going, right? And the question is it converging to something? So the picture you can see here as we go, it looks like it's going up and up and up, but doesn't it look like it's kind of flattening out there? Almost like, and again, like a horizontal asymptote. It's getting closer to something here.
To 1?
It looks like it's getting closer to 1, right? Let me go out 100 instead of there. So go out to 100. Okay, so if I go out to 100, you can see that they They flatten out. They don't look like they're ever getting bigger than 1, do they? Right? So how would we determine that? Well, we would have to take the limit as n goes to infinity of n plus 1 over n plus 2. And then we could just look to see, like, you know, what's happening. The numerator is going to infinity, the denominator is going to infinity. We have infinity over infinity, where normally we would want to use like L'Hopital's rule. But I mentioned last time we cannot use L'Hopital's rule because this is not a function. It's just a bunch of dots. So the idea of a derivative doesn't make sense. So the only way we could do this right now is to go back to a technique in Cal 1 where what we do is we multiply the top and bottom by 1 over n. And this is kind of like a trick that we learn in Cal 1, that if we multiply the top and bottom by, in this case, 1 over n, what happens is we distribute, we get this new limit of, let's see, when I distribute through, I get 1 plus 1 over n. On the bottom, I get 1 plus 2 over n. And now if I let n go to infinity, I can see that this piece goes to 0 and this piece goes to 0. And so all I'm left with is 1 over 1, which is 1. Are there any questions? So I'm going to do a different sequence. We talked about the sequence last time, negative 1 to the x, negative 1 to the n. Remember that one?
The
So in
alternating.
this case,
It was the alternating one, right?
so in this case, would it converge?
Which one?
The
Oh, yeah. For this one, it would converge to 1. Yeah, sorry. This would converge. And what does it converge to? It converges to 1. So the way we would write this, we could write it like this: n plus 1 over n plus 2 with an arrow to 1. That's the way we do the notation for saying that it converges to 1. So as n gets really big, this ratio gets really close to 1. All right, so do y'all remember last class the sequence negative 1 to the n? Right, the sequence negative 1 to the n looked like this. A sub n is negative 1 to the n. We said that sequence, when you plug in 1, you get negative 1, then positive 1, then negative 1, then positive 1, then negative 1. So when we look at that, here it is. I'm going to start putting it here. Oh, I need to zoom out a little bit. There you go. So you can see in the beginning, we're at negative 1 when we plug in 1.
Is it me or did he just like pause?
I was
He's
just
not in.
about to ask that.
I think he was like checking his phone and then he lagged out.
That's what it looks like.
Are y'all still there?
Yep.
Okay. Look, I don't know if you can see my screen here. See that? That blue screen of death. So my PC's rebooting. This has happened to me before. So once it reboots, I'll jump back in. It's probably going to be a few minutes.
That's
Sorry.
fine.
Yeah. While it's rebooting, think about, you know, does that sequence negative 1 to the n, does it converge or not? And, you know, how would you do, if you try to do that limit, it'd be kind of weird, right? So, okay, I'm gonna close out here because my PC's already coming back up. So let me get this thing going. I'll see you in a minute.
Okay.
Okay. See if it remembers where I was. Okay, kind of. Can you all hear me okay? We good?
Yes.
All right.
Yes.
Yeah.
Okay, yeah, so it doesn't remember the sequence, but let's get off the website. Let's just talk about that sequence. So a sub n equals -1 to the n. The graph, well, you know, I wanted you to see the plot, so hopefully this won't cause the issue again. -1 raised to the n. Let me draw this back a little bit. Okay, so it's up, you know, it's up here. Got to change one more thing. One. So it starts out -1 and then 1, -1, and it just keeps doing dots on top and bottom, back and forth. So when you look at that, do y'all see that that is not converging? Because you can't say it's converging to 1 because it's going to jump down to -1 on the next one that you go to, right? And you can't say it's -1 because it's going to jump back up to 1. So it's, you could say it's kind of converging to 2 different places, but to be convergent, you have to be going to a number, a single number. So it doesn't converge. All right, so this right here diverges. And that we would just say it diverges just by inspection, okay? Just by looking, okay? We'd realize it diverges. What about this one? A sub n equals -1 to the n times 1 over n. So let's write out the first few of these. First, we know it's alternating because it's -1 to the n. So it's going to be negative then positive, negative then positive. But then it's 1 over n. So when we plug in 1, we should get -1. What happens when we plug in 2?
Positive 2.
Positive
1 over 2.
The next one will be negative, but it'll be negative 1 over
3.
3, and then positive 1 over 4, right? So this is alternating also, right? It's changing signs, but just because it alternates doesn't mean that it diverges, as I'll illustrate here. So if we do this times 1 over n, there's the graph there. So again, it starts out, it's alternating positive, negative, but from both sides, it's headed towards 0. Do y'all see that? Okay, so the limit here is 0. So what we need is a way to calculate these limits easily. All right, because I told you, like, we can't use L'Hopital because these are sequences, right? So there's a theorem, okay? Now, theorems in math are mathematical statements that have been proven to be true. All right, so these are like, whatever statement I put here has already been proven mathematically to be a true statement. So here's what the theorem says. If you're given a sequence, a sub n, okay, then consider the function f of n equals a sub n. If the limit as n goes to infinity of f of n equals L, then a sub n also goes to L. Okay, so I need to be clear. There's some subtleties in here that I need to make sure you understand. This is saying that we're given a sequence, right? That's a sequence. A sequence is a function that has a restricted domain where you're only plugging in 1, 2, 3, 4, 5, 6, 7, right? It's saying for us to not consider the sequence, instead look at the function that is defined to be that sequence. And that means we want to look at that where the domain, the things that you are plugging in, are all numbers from 1 to infinity. So this is saying for us to, you know what, let's look at it as a function. Let's not look at it as dots. Let's look at it as a smooth function. Whatever that function does, the sequence should do the same thing. Does that make sense to you? Look at it this way.
I mean, hypothetically, it's the same thing, right?
It's not the same thing, but it is the fact that the dots were made up from taking a curve and just picking off certain points, then whatever the curve does, the sequence should do. But we can't say that they're the same thing. Sequences and functions are not the same in generally.
So is it like connecting the dot? Is it going to be like that, or they're like different slopes of a different curve?
Look, let's just go through this example. If we have a sub n is 1 over n, we already know that goes to 0, right? We already know that it does that. What this is telling us to do is don't look at that. Look at the function f of n equals 1 over n. And if you don't like that, you can just switch the n to x so it looks like something that you're more familiar with. Just look at the function f of x equals 1 over x. Graph that, whatever that one does, the sequence should do. So it's telling us to say, all right, we are going to look at the function 1 over x, okay, which is there in blue. So the blue is 1 over x, and the dots are 1 over n. So do y'all see that whatever, oh, sorry, I need to get rid of that -1. Okay. Yeah. So can you see that whatever the blue curve is doing, the black dots have to follow?
So
right?
it is the same path.
It's the same path. It's the same. The limit of the function is the same as the limit of the sequence. That's what the theorem is saying, right?
Mhm.
Okay. So it's a great theorem because what this theorem allows us to do is use L'Hopital's rule if we need to. Okay. So
Just to take a reference.
yeah, it's going to help guide us. We're going to see, though, it doesn't work for everything, though. Okay.
Okay.
So it's helpful, but it doesn't solve all our problems. So here's another example. Let's go back to the one that we had before. A sub n equals n plus 1 over n plus 2. Okay, we showed that that goes to 1, right? But I had to multiply by 1 over n top and bottom. Instead, what I'm going to do is I'm going to look at the function, and I'm going to say f of x. I'm just go ahead and go to f of x. Is x plus 1 over x plus 2. Now that function, if the limit exists for this as I go to infinity, then this one should do the same thing. So let's see, if we take the limit as x goes to infinity of x plus 1 over x plus 2, we know that that goes to infinity over infinity. So I'm going to use L'Hopital's rule now. See, now I'm allowed to. See, I'm allowed to use L'Hopital because I have a function. a nice continuous function. I don't know what's going on with my voice today. So I take the derivative of the top and bottom separately. I get 1 over 1, which is 1. Okay. So the theorem says, therefore, did I show you the 3 dots last time? I don't think I did. You're going to see me use this. When you see me put 3 dots like that, that means therefore. That's mathematical notation. I didn't just make that up. Okay. Mathematicians use 3 dots like that, like a little triangle, to represent the word therefore. So therefore, what I can say is that n plus 1 over n plus 2 also goes to 1. So it converges. All right. All this theorem does is allows you to use L'Hopital's rule. That's all it does. Okay. Now, there are limitations to this rule. How about we do this one?
And Professor, when should we looking at, say, infinity, or in this case, just 1, because 1 is the limit, but it's actually going to infinity, even though the boundary is 1?
No. The inputs are going to infinity, right? The inputs, what's going into the function is going to infinity.
Uh-huh.
The output is headed towards 1.
Or it's getting closer to 1.
Yes, the output of the function is headed towards 1.
Okay.
As the inputs get big, the outputs get closer to 1. Okay, so look at this one here. If we were trying to find this, and we did this one a second ago, the dots were going up and down, right?
Mm-hmm.
Let me put it back in here. Raised to the n. That was it right there, okay? We can see it's going to 0, but, right, it's going to 0. But what's wrong? Can I put that function in here? What if I try and type this function in here in terms of x? So if I go times -1 raised to the x. Where's the graph? What the hell's going on? There's no graph.
Is
Why
it
is
because
there-
there's no value for x determined right now?
Think about, yeah, think about the function f of x. Whoa. Think about the function f of x equals -1 to the x times 1 over x. All right, now if I plug in nice numbers like 1, 2, 3, 4, 5, of course I can figure out what this is, right? But why don't you try plugging a number in like 1/4 or 1/2? Let's just go with 1/2. What would happen if I try and plug 1/2 in here? -1 to the half times 1 over 1/2, right? This part's okay. 1 over
Right.
1/2, that's just 2. But this means the square root of -1, right?
But we can't do that.
We can't do that, right? In fact, there's a bunch of things we can't do to -1. We can't raise it to 1 over, we can't raise it to a half. We can't raise it to a fourth. We can't do any even roots of that. And when you think about it, so by trying to extend this sequence over to a function where your inputs are real numbers, you can't. Does that make sense? You can't do it. So we cannot use the theorem. Do I need to clarify, or is that clear enough?
So if the inputs of a sequence are real numbers, then we won't be able to do the L'Hopital's rule.
If your function is not defined for certain values of real numbers, then you can't use it. See, we have a domain problem. We can't plug certain numbers into this function. And that's why the computer doesn't even try. Like the computer doesn't even try and draw it because it realizes it can't. All right, it realizes that you cannot -1 to the x's. Do y'all remember when you were learning exponential functions? When you back in college algebra, you were taught that an exponential function looks like a to the x. Okay, and you were told in that class that there were some restrictions on a. And one thing you were told is that a had to be greater than 0 and a could not be 1. So they tell you that a can't be 1 because 1 raised to any power is 1. So they just take this out a being 1, they take that out because that's a very boring function. And then they force you to put a positive number down here. And the reason is because if you put a negative number down there, there is no graph. There's all sorts of problems. So that's why when you define exponential functions, your base must be positive. Here, what we've done is we've tried to create a function where our base here is negative, and that is just undefined. Okay, so even though this is useful, this theorem, it's not going to save us all the time. Let's do another example. Okay, this one is an interesting one. So 1 plus 1 over n raised to the n. So there's the sequence, right? Let's just see if we can figure out what's happening. If n gets big, right? If n gets really big, this thing here goes to 0, right? And this thing here heads to infinity. So what you have is something that looks like this. It's 1 plus, well, I'm going to put 0 here, but it's not really 0, and then to the infinity. What we all have to understand, though, is this number in here is not really just 1. And that's because 1 over n is a tiny, as n gets really big, that's a tiny little number, isn't it? And so this number, you could say this number right here is just a little bit bigger than 1, right? That number right there is just a little bit bigger than 1. And then we're raising that to something that's becoming infinitely big. And back in college algebra, this is referred to as an indeterminate form, right? This is just like getting 0 over 0 or infinity over infinity, right? These are things we cannot tell what the answer is. So we have to have a way of figuring this out. All right. Now, you may have done this in Cal 1, maybe you remember, maybe you don't, but the first thing I'm going to do is I'm going to convert this over to a function of x. So I'm going to say, all right, let me try and look at it as a function of x first. Now, this is a well-defined function. There's no problems with me plugging numbers into this, with the exception of 0. I can't plug 0 in. But I don't care about 0 because I only want to know what this function is doing from 1 to the right. Because my sequence is going to start at 1, isn't it? The sequence starts at 1, so I don't care about anything to the left of 1 at all. So I don't care that 0 is an issue for the domain here. All right, so let's try and figure out what this is doing. I want to find now the limit as x goes to infinity of this. And since that is giving me the form of 1 to the infinity, and we know that's an indeterminate form, I need to do something. So this will go back to, again, how you were taught this. Here's how I teach my Cal 1 students. I say, whenever you have a form 1 to the infinity, you always just set the limit equal to something. So I'm just going to call that limit y. And then I bring in the natural log on both sides. So I basically apply the natural log function to both sides of the equation. And what does the natural log allow me to do? Does anyone remember why that natural log is brought in?
So you can take the x in front of the natural log?
That's right. I can bring the power and I can drop it out front. That's a property of logs. So when I do that, I now get natural log y equals the limit as x goes to infinity of x times natural log of 1 plus x. And now what I do is I look and see, what is this limit doing? All right, so this is now headed to infinity. Let's see, the inside of this is headed towards 1, right? And what is natural log of 1?
0.
0. So what we get now is another limit that has the form of infinity times 0. And that is still an indeterminate form. You've got one number that's getting big and the other one is getting small. Remember, this is not, we're not saying that this part over here is 0. We're saying it's approaching 0, right? So you got a number that's getting really big times a number that's getting really small. Who wins, right? Who wins the battle? Well, we have more to do. So does anyone remember what you do when you have a limit where you have this form?
Drop one down.
Drop one down. So take one of the two
Yeah.
and drop it to the bottom. So
No.
I'm going to take the x and drop it to the bottom. And what we mean by that is you rewrite it as 1 over x on the bottom. So an x on the top is the same as putting a 1 over x on the bottom, because that would just reciprocate and come back up. But the advantage of doing that is that now when I take the limit again, we already know that this natural log thing is headed to 0, but 1 over x, that is also headed to 0, and you have division. So now you finally have it in the form 0 over 0. Now you can use L'Hopital's rule. Okay, so I'm about to use L'Hopital, but let me just recap. If you have 1 to the infinity,
How did you get 1
Hold on.
over x?
hold on. If you have 1 to the infinity, you put, you set your limit equal to something. You take natural log on both sides, so you can drop this thing out. Once you do that, you should get infinity times 0. You pick one of them, you drop it down, and then from there you should get 0 over 0. Okay, what was your question?
So how did you get 1 over x? I thought it was just x.
It's just algebra. It's just the algebra. Look, if you have 1 over x on the bottom, if you could flip that back up to the top, couldn't you? Like if you bring
Oh,
that
yes.
up, it would come up and it would become an x, right?
Mm-hmm.
I did the opposite. I took the x up there and I dropped it down as a 1 over x. So I just did it backwards.
Is
And that's the standard kind of technique. I heard another question.
in the parentheses, isn't it supposed to be 1 plus 1 over x?
Oh, I forgot to put 1 over x, didn't I? Oops. Thanks, CJ. Appreciate that. Yeah, this is 1 over x. That would have caught up to me in just a second here. That's 1 over x. That's 1 over x. My apologies. Everyone see that? I'll highlight it. I put x there. I don't have no idea why I did. These limits are correct though. This goes to 1 because 1 over infinity goes to 0. Okay. And 1 plus 0 is going to head towards 1. So that's correct. And then natural log 1 heads towards 0. Okay, now L'Hopital. So I come in here, I'm going to use L'Hopital, so I'm going to put an L there. Limit n goes to infinity. Now derivative of top and bottom. Okay, derivative of the top. The derivative of natural log of something is just 1 over that something times the derivative of what's inside. So I take derivative of 1, right, which is 0, plus the derivative of 1 over x. Remember, 1 over x is the same as x to the negative 1. So when I take its derivative, I get negative x to the negative 2, which is negative 1 over x squared. We're all this far in this class, so we should all be comfortable with this, right? So this is negative 1 over x squared is what comes out here. And then I take derivative of the bottom. What's derivative of the bottom?
1.
It's the same, it's 1 over x again, right? So we have to take derivative of that, which is negative 1 over x squared again, isn't it? So these
Cancel out.
right? And
Negative
now take the limit. Let x go to infinity. Boy, I'm having one of those days. X go to infinity, not n. Let that x go to infinity right there. Everything else is gone. What would you get on the right-hand side if you do that limit then?
0.
1 over
0.
1 plus 0, right? This becomes 1 over 1 plus 0, which is 1, right?
1 over 1. Convert.
So here's what we're saying. All of this work, we're saying that natural log of y is 1. But what are we trying to find? Oh, we're trying to find this, right? We're trying to find this. And wasn't that y? That's what y is. Y is the thing we're looking for. So I need to know what y is, not what natural log of y is. I need to know what y is. So I need to figure out what this y is right here. So all I'm going to do now is I'm going to go backwards and I'm going to undo the natural log. So I'm going to bring e in on both sides. And the e and the natural log kill each other off, and we get y equals e to the first power, which is e. So the limit, that limit is E. So the answer to this now, what I can say here at the end is therefore, the sequence 1 plus 1 over n to the n converges to E. So the bigger and bigger n values you plug in, the closer and closer it's going to get to the value of E. In fact, E is defined to be this limit. Okay. I have one more and then we need to move on. God, there's just not enough time in this class. We just do not have enough time. All right, so I'm going to give you a sequence here and I want to see if we can figure out what it converges to. The sequence is the square root of 3 and then the square root of 3 square root 3 and then the square root of 3 square root of 3 square root of 3 and then the square root of 3 square root of 3 square root of 3 square root of 3. Okay, does this sequence converge? Does it converge or does it diverge? So what are you going to need to do first?
Convert
Find
it.
A of n.
Yeah, we have to find the sequence. We have to figure out what the hell the formula is for this sequence, right? And then whatever formula we get, we're going to take the limit as n goes to infinity. Okay, that's what we're going to do. All right, so right now you should be looking at that. You should have a headache because that's weird looking. So let's just go back and change these. This means 3 to what power?
1 over 3.
One half, right? That's the square root of 3. What is this one? Well, let's see. We have the outer square root, right, which is 1/2, and then we have 3 times 3 to the half. So I'm rewriting this big square root is this half on the outside with the big parenthesis. Then I have 3, and then I have square root of 3 again, which is 3 to the half. So can you put these two together? How would you put those two together? You have to add their exponents, right? So isn't this 3 to the 3 halves to the half? Right? 1 plus a half is 3 halves. And then you have this power here. Now, how do we do this? Something to a power to a power. What do you do to these powers?
Multiply?
Multiply them. I'm running out of room. Here, let me see if I can't move this down. Yeah. Oh, that didn't work. I may not be able to move this down. Oh, well, I'll leave it up there. Okay, so what does that one become? 3
To the
3 to
fourth.
the 3/4.
Fourths.
Okay, the first one was 3 to the 1/2. Okay, let's see if we can't figure out the rest of this. So let's be clever. Do y'all know what this is in yellow? What is that?
3 to the 3/4.
Yeah, that's the one right before it, isn't it?
Mhm.
Okay, so this would be the square root, okay, of this 3 right there, times everything in yellow, which we just said was 3 to the 3/4. Now we put those together. So what happens when you add 1 and 3/4 together? What do you get? 7/4. And then we have that to the half. Multiply these two together, and we get 3 to the 7/8. Okay, let me write the ones that were in front of it. 3 to the 3/4. The one in front of that was 3 to the 1/2. Okay, keep going. Should we keep going? All right, so next one. Now, everything in blue here, everything in blue is the previous answer, isn't it?
Mhm.
Okay, so that should be then, again, a big square root or big parenthesis raised to half. We have a 3 to the first power. That's this piece. And then everything in blue should be 3 to the 7/8. And so let's see, we put those together, 3 to the, what is that, 15/8?
15/8.
And then we have that raised to the half. So we multiply and we get 3 to the 15/16. Any predictions on what the next one would be? Do you all see the pattern? What would the next one be?
32, it's gonna be to the 32 seconds.
30 over 32.
What over 32?
30 over 32.
30, that's close. It's not 30.
31 over 32.
31 over
31
32.
over 32. The next one?
62 over 63.
64.
63 over 64.
63 over 64.
So here's the pattern you have to understand. The base, the denominators, all these denominators are powers of 2, right? That's the pattern. 2, 4, 8, 16, those are powers of 2, and the numerators just seem to be one less than those. Do you agree? Just one less.
Yes.
So can we come up with a formula? A sub n. Well, we know the base is always 3. And then we have a fraction here. Okay, I'm going to put the fraction like this. The denominator is just 2 to a power, right? So 2 to the n. Do you all agree with that? Do you agree with that? That's what these things in yellow are. This would be 2 to the first, 2 squared, 2 cubed, 2 to the fourth, right?
Mm-hmm.
And then what's the numerator?
2 to the nth minus 1.
2 to the n minus 1. So it's the same as the bottom, but just take 1 away when you're done. And there is our sequence. That should generate that sequence. Now that's not our answer, right? Now we need to take the limit. What is the limit as n goes to infinity of this?
Not to be rude and interrupt, but I noticed that since your computer restarted, did you restart recording by chance?
It says I am.
Oh, okay, okay.
Yeah, no, it's okay. I looked at that when I came back. It looks like it was recording the whole time I was gone.
Okay, cool, cool.
I
Just
hope
making
y'all
sure.
didn't say anything that you shouldn't have. Okay, here's where we are, right? We need to take this limit. And so notice that the top goes to infinity here, right? 2 to the infinity minus 1 is still infinite, and the bottom goes to infinity. So do you all see that we have kind of like an infinity over infinity here? Right? So I'm going to use L'Hopital's rule. But to use L'Hopital's rule, I have to do this limit. Limit x goes to infinity of 3 to the 3 raised to the 2x minus 1 over 2x. I'm switching it to x instead of n because I can't do L'Hopital with a sequence. I have to do it with a function. So I switch it to a function of x first. And now I'm just going to focus my attention on what happens to this, right? And use L'Hopital's rule. Because it's infinity over infinity, I can leave the 3 alone, and I can just do derivative of top and bottom separately. Does anyone know what the derivative of the top is? What's the derivative of 2 to the x? Don't tell me x times 2 to the x minus 1. Don't tell me that. Don't pull that x out front. This is not a power function. This is an exponential function.
It's just 2 to the x.
2 to the x, almost, times, you have to throw one more thing in there.
2.
Natural log of 2. This is Cal 1. This is the derivative of an exponential function. It's on your formula sheets, okay? It's derivatives, where are they? Right here, derivative, right here, formula 10. The derivative of a to the x is itself a to the x times natural log of a. So that's what I'm using there. Okay, that's the derivative of that. So do y'all see that the derivative of the top, because it's -1, that's the derivative, that's going to be 0. So you just get on top there, 2 to the x times natural log 2, and then the bottom, 2 to the x natural log of 2. So I just took derivative of the top and bottom there. And don't those go away? I mean, don't those just cancel? Don't you get a 1? And so our answer is 3 to the 1, which is just 3. Which means that the limit of this sequence is 3. It converges. So if you were to get on your calculator and start doing this, like what's the square root of 3, and then take the square root of 3 times that answer, and then take the square root of 3 times that answer, and then the square root of 3 times that answer, and keep doing that, you could, if you could go to infinity, your answer would get closer and closer to 3. Okay? Do you believe that or no? Maybe I can do it. I can just do it here. It was 3 raised to the 2 raised to the n minus 1 over 2 raised to the n. There we go. Where are you? Come here. There you are. There's the sequence. There it is. Okay, we plug in 1, plug in 2, plug in 3, 4, 5, 6, and look at it, just like starts flattening out towards 3. That's an interesting problem. Okay, we are going to continue this section.
When are we having the test again?
Okay, so if you came in a little bit late, I started class with this information. The exam is going to be a take-home exam. It's going to be sent out at the end of class. I'll talk about this at the end of class. If you need to go back and do this. Okay, so now we need to do some more. We're still in 8.1, unfortunately. This section just takes forever. We need to get some definitions. Okay, so I'm going to create here a definition. Okay, a sequence is called increasing if a sub n is less than or equal to no, just strictly less than, sorry, a sub n plus 1. So what does this inequality mean? It means that if you look at a certain term of the sequence, like let's just say, for example, you were looking at the 4th term of the sequence, then the next one, the 5th one, would have to be bigger than the 4th one. So what's happening is you go out in the sequence, each dot is getting a little bit higher than the one before it. Okay, just a little bit taller. Any sequence that does that is said to be increasing. So it's just like a function, right? Just it's going up as you go from left to right, it's going up. Similarly, it's called decreasing if what? I'm not going to rewrite all that. It's called decreasing if what? Just the opposite, right? The nth one is bigger than the next one. So as a specific example, if the 4th one is bigger than the 3rd one, sorry, not the 3rd one, the 5th one. So the one before is bigger than the next one. That means that they're getting smaller as you go from left to right. And that means it's a decreasing sequence. Is that pretty straightforward? Understand? Okay. In either case, a sub n is called monotonic. All right, so right now, if I were to tell you, hey, we've got this sequence, okay? I'm going to tell you about this sequence, really special sequence. It's a monotonic sequence. As soon as I say monotonic, I'm telling you that it's either increasing or decreasing. All right? It does, monotonic doesn't tell you which one it is. It just tells you that's one or the other. Okay? With me? Next definition. A sub n is said to be bounded above if there exists. Now in math, we don't like to write there exists because we have to say that so many times in pure math. There's actually a symbol we use for there exists. It's a backwards capital E. That means there exists. So if there exists a capital M such that A sub n is less than or equal to capital M for all n. So the way I want you to think about bounded above is that to say a sequence is bounded above means that it has a ceiling, okay? There's a value that it never goes past. If you look back at this right here, would you all agree that this sequence is bounded above? Okay, it's bounded above because there exists a number that this sequence never reaches. You could say 3.5, couldn't you? Like it never reaches 3.5. So capital M could be 3.5. You could also say capital M is 3.1 because it never reaches 3.1, right? You could also say 3 in this case because it actually never reaches 3, but this sequence is definitely bounded above. Now, do you think this is an increasing or decreasing sequence?
Increasing.
It's increasing, right? It's increasing. So you have an increasing sequence, but it's bounded above, which is kind of weird because you're saying there's a ceiling, right? But each time you move out, it goes up a little bit more, but there's still a ceiling. Like you can keep moving as far as you want and it'll always stay below that ceiling.
So
But
is
that's
it
okay. I mean, that's what an asymptote is. What do you got?
so is the ceiling 3 then?
No, 3 is a ceiling, but any number from 3 or above would be a ceiling. So when you look at this definition, it says, look, there just has to exist at least one number that it always stays below, all right? So you can have multiple ceilings. Any number above 3 would be a ceiling. All
Okay.
right, so what about this? A sub n is said to be bounded below if what? Same idea, right? But it's now on the bottom. If there exists a little m such that our sequence is always bigger than or equal to little m for all n. So no matter which number in the sequence you pick, it always stays above some number. We say a sequence A sub n is bounded if it's both bounded above and below. Okay, so we have 3 definitions here for this little thing. We have bounded above, bounded below, and bounded. Oh, sorry, and bounded. Bounded above means there's a ceiling. Bounded below means there's a floor. And bounded means there's both a ceiling and a floor on your sequence. So when you go back to this sequence here, is this sequence bounded above?
Yes.
Yeah, right?
Yes.
There's a ceiling. Okay, is it bounded below?
No.
Does that sequence, is there a number that sequence always stays above? Always?
Negative
I need to zoom out a
3.1.
little bit more. Hold on.
0?
Negative.
Yeah, 0 would work, right? I mean, definitely this sequence starts right here, right? So you could say 0 is a floor, couldn't you? You could also say 1 is a floor, even 1.5. See, do you see that this sequence is stuck between these things? It's bounded,
Mhm.
right? It's bounded above and below. Bounded above and below. It's also monotonic. It's monotonic increasing, right? Because as you move from left to right, it goes up as you move from left to right. All right. Now,
Is there such thing as non-monotonic?
oh yeah, oh yeah. Sequences do not have to be monotonic. If you take the sequence, look at the sequence here, a sub n equals sine n. What that sequence looks like is this. It looks like the sine, well, it looks like the sine curve, right? Like this is the sine curve. But we're only plugging in 1, 2, right? So what you're going to wind up getting are just a bunch of dots that live on the sine curve.
Mhm.
This is not monotonic. Yeah, it does go up for a while, but then it starts going down, and it starts going back up and start going down, right? So this is not monotonic at all. But it is bounded above and below, right? So it's definitely a bounded sequence, but it's not monotonic. Yeah?
Okay.
Okay, so let's take a look at a sequence here. And I'm just going to give you this. Okay, show a sub n is bounded. That's first thing. Next thing, is it monotonic? I always think that the best thing to do is just to start writing a few of the numbers out in the list. So let's just plug in 1. If we plug in 1, we should get 0. If we plug in 2, we should get 1 minus a half, which is a half. If we plug in 3, we should get 1 minus a third, which is 2/3. If we plug in 4, we should get 1 minus 1/4, which is 3/4. Plug in 5, we get 1 minus 1/5, which is 4/5. And this keeps going, right? I would say it's definitely bounded below, right? I mean, look at all these numbers. They're all positive, right? So here's what I'm gonna do first. I'm gonna show it's bounded below. Here's how I show it. I have to show you, okay, so I'm gonna write this down. I want to show, WTS stands for want to show, okay? Want to show, that's what WTS stands for. I'm gonna use that a lot through the rest of this chapter. All right, so I need to show that it's bounded below. So to do that, what I wanna show is that there exists a little m such that, I'm using the definition, such that a sub n is always bigger than or equal to little m for all n. So the stuff we're going to start doing in here is going to start looking very mathy instead of just like algebra and computations. We're actually going to have to like write out what we're thinking and show our processes. All right. So I'm first showing that it's bounded below. To do that, I have to show there exists some number that's always below my sequence. What do we think that number is?
0.
Zero.
0. Okay, 0 would work. So I'm going to now say let little m be equal to 0. And now the question becomes this question right here. Is this inequality true? Is it true? So let's write it out. The inequality is this. 1 minus 1 over n is bigger than or equal to 0. And this is what I need to check. Is that true or not? Right? That's what I need to show. Okay, well, here's how I'm going to do that. I'm going to add 1 over n to both sides. And then I'm going to multiply both sides by n. Any questions on that algebra? Move the 1 over n over, add it to both sides, multiply both sides by n, and I get this. Hey, wait a minute. When you have inequalities, don't you sometimes have to flip the inequality over? If you do something, if you multiply both sides by negative or divide, don't you have to flip the inequality over? You do. But I know, what do we know about n? What do we know about n? N is the input, isn't it? Remember, the n is the input, and n is going to start at 1, then be 2, then 3, 4, 5, 6, 7, right? So I know that when I multiply both sides by n here, I didn't have to worry about flipping the inequality because I know that n's not negative. And now we get to this final statement, and this statement is true. Why is that true? Again, because n is going to be 1, 2, 3, 4, 5, 6. So yeah, of course, n is always bigger than or equal to 1. So what you're trying to do is you're trying to confirm this inequality is true by doing some algebra on this inequality to get a final statement that actually makes sense and everyone agrees with. Yes, n is bigger than or equal to 1. We're happy. All right, now let's show that it's bounded above. Maybe it is. I don't know. Do y'all think it's bounded above? These are all fractions, right?
Getting
It
smaller
doesn't
and
reach
smaller
1.
though.
It never reaches 1.
You don't think it reaches 1? Okay, so if we don't think it reaches 1, then let's say that that's our upper bound. Okay, let's go for it. So I want to show it's bounded above. Right, so that means I want to show there exists a capital M such that my sequence always stays smaller than or equal to that m for all m. I have another shorthand notation for y'all. Y'all see this for all? We have a notation for that also. It's an upside down capital A. For all n is written this way. I'm just sharing. I know there's maybe like 1 or 2 of you who are math people, like want to do math. So that's kind of giving you a preview here. Okay, so let me take this to the next page. Okay, here we go. So I want to show that there exists some capital M such that my sequence always stays smaller than that. Abe said he thinks that 1 is our upper bound. So let's let capital M be 1. And now let's try and show this is true, that the sequence is less than or equal to 1. And that's the question, right? Is this true? All right, so I'm going to do something a little different here. How about I move the 1 over n to the right, and then I subtract 1 on both sides. So I'm going to move that. Oh, shit. What did my computer just do? Okay, move that over to that side, and then I'm going to subtract 1 on both sides. So what I wind up getting is the left side is 0, and less than or equal to 1 over n.
You did it because so that you don't have to then flip over the sign.
Yeah, I just did it to avoid a negative sign. Yep. At this point, we could probably stop and say we all agree that's true, because n is a positive number, isn't it? It's either 1, 2, 3, 4. So if I take a positive number like 1 and divide it by a positive number, then I know that that's always going to be a positive number. So I know the left side is positive no matter what. And anything that's positive is bigger than or equal to 0. right? So I could say that I'm happy here and I can say, yes, that's true. Or I could multiply both sides by n. If I multiply both sides by n, what do I do? What do I get?
0,
You get 0 is less than or equal to
1.
1.
1. And is that true? Well, I hope so,
Yes.
right? Either way, you want to get to a point where it's obvious that it's true. So this is a bounded sequence, isn't it?
Mhm.
This is a bounded sequence. We've shown it's bounded because we've shown it's bounded above and below. You have to be both to be called bounded.
How
Now-
can we tell when it's bounded on the y and x and not both on x?
I'm not sure I understand your question.
So there's two limits, or whenever it's bounded, it's always like, in this case, it's always at, what was it, 1? Yes, at 1. So our limit on the top, the ceiling was 1. And then this other number that we proved, how can we tell that that's actually on this axis and not at the bottom, perpendicular to our other limit?
I'm not sure. Does anyone understand the question? I'm trying to interpret the question.
So the only places that are being bounded are on the top and the bottom of a sub n.
Yes.
So the limits would never be perpendicular to each other.
Okay.
Like
Yeah,
like
because
the,
remember-
like the
yeah.
bounds would never be perpendicular.
Okay, now I understand, I think, what you're saying. So whenever we talk about bounded, we're only talking about bounded above and below. You don't talk about bounded left and right because we know it's bounded to the left because the sequence starts at 1. And we know that it goes forever because those dots do something forever to the right. So we're not even considering trying to bound it that way. It's only, and remember, a sequence, we're only looking at the outputs, right? The outputs is what the sequence is. It's the outputs. This is just a visual representation of those outputs. We just want to make sure those outputs are stuck between two different things, two different horizontal lines. Now, are we saying, just be real careful with this, are we saying by saying this right here, are we saying that this sequence is approaching 1? Is that what this, can we draw that conclusion that this says that the sequence is approaching 1? No. All we're saying is that the sequence doesn't go past 1, right? If someone else, Abe was the one who said, let's use 1, right? But if someone else would have used the number 4 here, then this would have been 4 here. And then I would have subtracted 1 on each side, or sorry, I would have subtracted 4 on each side. And then this side would have been -3. And we would have moved this over and we would have 1 over n is bigger than -3. And that still would have been true, right? That doesn't mean that our sequence is headed to 4. It just means it never gets to 4. 4 is a ceiling. There's going to be if your sequence is bounded above, you're going to have an infinite number of ceilings. You just have to find at least one to say that it's bounded above. Does that make sense?
Okay, question.
Yeah.
So in the previous exam, when you were doing the lowercase m, why did you bound it to 0?
I didn't. Someone else gave me that.
Oh, okay.
Yeah. Someone.
So like that,
I
we can
asked
do it
someone said
with
0.
anyone.
What's that?
So I'm saying that so we can use any number as long as it say it's true.
So like,
Okay.
if you look at this sequence, if I were choosing a lower bound to try and show that it's bounded below, I would have probably chosen -1 because none of these are negative, right? So -1 should have worked also. And if you run through the algebra here and you replace that with -1 and do the algebra, it'll come out to be true. Again, that doesn't mean that we're approaching -1, just means our sequence never goes below -1.
Do we necessarily need to pick the first, call it the first level or the first ceiling to prove this point?
Do you have to pick the first one?
Yes, because you said like on the last example, we picked 1 and then you selected 4, And you said that is also true because there's different levels of ceiling. Do we need to pick the lower ceiling? The
No,
close, no?
no,
Okay.
any ceiling. If you want to know what the lowest ceiling is, that's called the least upper bound. And that's a very difficult question. How to find the least upper bound is very challenging.
Okay.
Then we would have to try and error with different numbers.
It's called it's actually called the limp soup. Okay, that's what it's called, the limp soup. It's called the limit of the supremums. So in other words, all of these horizontal lines are ceilings, right?
Mm-hmm.
And so we call these supremums because they're supreme to the sequence. They are above the sequence, right? And what you're trying to find is the limit, the one that's closest to your sequence. And that's called the limp soup. So it's like a limit of the supremums. What are the supremums approaching? And that's a very difficult question in general. All we're trying to find is just one ceiling. Just show me it's. Now, let me show you why, okay? Let me get through this example. I'll show you why it's useful to be able to show that a sequence is bounded and that it's monotonic. Right now, all we've shown is that it's bounded, right? That's all we've shown? Okay, now, the other question was, is it monotonic? So look back at your sequence. Does it look like from this sequence that as you move through it, each one is getting bigger or are they getting smaller? 0, 1,
Smaller.
2/3. Is 2/3 bigger than 1/2 or smaller?
Bigger,
It's bigger. Is 3/4 bigger than 2/3 or smaller?
bigger.
Bigger. 4/5 is bigger. It looks like this is an increasing sequence, doesn't it? They're getting bigger as you go. So I have to see that, and now I have to say to myself, is it monotonic? I think yes. I think it's increasing. Okay, I think it's increasing. I'm not quite sure. I think it is. It looks like it is. So if it's increasing, what do we have to show? What does it mean to be increasing? Let's write the inequality out. Increasing means
A sub of n is less than a sub of n plus 1.
Yep. That's what it means to be increasing. The nth one is smaller than the next one. So that means I want to show that that's true. Okay, I want to show that's true. So can somebody tell me what the nth term in this sequence would be?
The first one.
No, not the first one, the nth one. Wouldn't that just be 1 minus 1 over n?
Oh, okay, yeah.
Right? Is that smaller than the next one? What would the next one be? 1 minus 1 over
minus 1. N plus 1?
Right? It's one more. So I'm replacing the n with n plus 1. Now I need to show that this is true. Is this a true statement, this inequality? Let's see. Let's subtract 1 on both sides. Okay, we have negative 1 over n is smaller than negative 1 over n plus 1. I don't like these negatives. So what I'm going to do is I'm going to move this one to the left and move this one to the right. So I'm going to add these on both sides. So now I get 1 over n plus 1 smaller than 1 over n. Now I'm going to like cross multiply, right? And what happens if I cross multiply? I get n is smaller than n plus 1. Is that true?
Oh, yes.
True? Yeah, that's true. You could subtract n on both sides if you wanted to now. And you get 0 is less than 1, and that's true.
So if I was looking at it in a way that if I don't shift the negative one onto the other side, then it's like, yeah, when you were shifting. So it looks like as if the statement is wrong.
Yeah, what you could do is you could multiply both sides by -1. Okay. But because you multiply by negative, you'd have to flip the inequality.
Oh, okay.
And so what it would turn into is 1 over n is now bigger than 1 over n plus 1. And then when you cross multiply, you get n plus 1 is bigger than n. And that's still true. Okay. This sequence is bounded, but it's also increasing, right? All right, and that brings us to the next theorem. And the last theorem, and we'll be done with this section. Theorem. The bounded monotonic sequence theorem. Okay, here's the theorem. Here's what it says. Every bounded monotonic sequence must, what do you think? Must do what? Anyone?
Like stay under a ceiling or something?
And we know, yeah, it will stay under ceiling, but think about this. Look at this sequence right here. Let's say I have a bounded sequence that does this, like the sine one. That's bounded, right?
It must be increasing.
Okay.
It must.
So
It
this
must
one right here is not
Increasing?
monotonic, though. This is not monotonic, right? What if I told you it had to be monotonic? That means it has to be either increasing or decreasing. So let's just go with increasing. So what if I had to draw an increasing sequence right now that had to be bounded? It would have
So
to
it will go to the right. Like
okay, but what
always.
would happen? It would have to
Oh,
do
it
what?
has to converge. It has to
Has to
converge.
converge. Very good. It must converge. So look, you know how we started this out and we were saying, hey, if someone gives you a sequence, we want to know if it converges or diverges. Sometimes it's very difficult to show a sequence converges or diverges. When you try and do the limit of the sequence, when you try and do this limit, it's like, crap, man, that's like terrible. I can't do the limit, it's too hard. So if you can instead show it's bounded and show it's monotonic, then you're done. You know it converges. You don't know what it converges to, but you know it converges. Which, believe it or not, is going to be enough for us. As we move on in this class, we're going to realize that there's a lot of things we can't figure out what it converges to, but what we can say is that it does converge. And that will be all really that we need to know. In the big picture of things, that's all we need to know is, do we have convergence or not? You'll see as we.
So for example, like you said about the sequences that we wouldn't be able to decide what they will converge to, does the calculator have an answer to that?
It might, yeah, we could probably do it on a computer, yes. All right, so there's a lot of problems in the homework for you to go through in this section. There's a lot for you to do. There's a lot of things, the algebra and the things that we're gonna call on from Cal 1 are things that there's just not enough time in this class to go through. So make sure you do the homework, and if you get stuck, make sure you're watching my solution videos for those problems so that you can get reacquainted with some of the algebra. But I will do one last example. This has nothing to do with the monotonic, bounded monotonic theorem. This is just a really cool example. So show that a sub n converges to 0. So I'm going to give you a moment to think about that. I'll be right back. I'm going to give you like a minute maybe to just think about what that sequence is doing and how you could show that it, see, this is saying show it converges to 0, right? That's what I'm telling you. Show that it converges to 0. So just think about how you might go about that. All right. I just wrote out the first few terms. Now, this is what we need to do. We need to take the limit as n goes to infinity of n factorial over n to the n, right? That's what we need to figure out. Is everyone clear with that? Now, if you let n go to infinity, does everyone agree you get infinity over infinity?
Yes.
Yes? Okay. Now, we've normally dealt with infinity over infinity by doing L'Hopital, right? We cannot do
Yes.
L'Hopital. Here's why we can't do
But
L'Hopital.
we can.
What? Were you saying something or no? Can someone tell me why we can't do L'Hopital?
Because of the factorial.
Yeah, what's the derivative of n factorial? It has no derivative. It has no derivative because n factorial is only defined on the integers, like 1, 2, 3. You can only do like 1 factorial, 2 factorial, 3 factorial. There's no way to convert this to a function of x. If you can't do it as a function of x, well, then you aren't graphing it, right? You don't have a nice, smooth, continuous curve, which means you can't take derivatives. So there's no workaround for this. All right? Now, we might be able to, the bounded monotonic theorem, right, that I just gave you, maybe we could use this, show it's bounded, show it's monotonic, but the problem with this theorem is that all it tells you is that it would converge. What are we supposed to do?
Show that it goes to 0.
We would have to prove that, and that's not what the theorem gives you. The theorem only gives you convergence, doesn't tell you what to. So this is the first time I'm going to show you something that is going to be somewhat weird, all right? Well, not the first time I've shown you something weird, but it's going to be strange the way I approach this. Okay, so let's take a look at what a sub n is. A sub n in general. I'm doing this in the middle of the page for a reason. A sub n is just, like, let's say someone gave us an n. This would be n factorial over n to the n, right? But that is just, well, what's n factorial? It's n times n minus 1 times n minus 2 times n minus 3. And I keep doing that until I get down to 1, right? Do y'all agree that's what n factorial means? Yeah? Okay, divided by, what does n to the n mean?
The power of.
So like, what would 3 cubed mean? 3 times
27.
times 3, right? What would 4 to the 4th be? 4 times 4 times 4 times 4, right? What's n to the n mean? It means
N times n.
times n times n times n. How many of them would I have?
N times.
I'd have n of them, right? And do y'all see that that is the same number of factors we have in the numerator? Yes? Okay, so we could almost like partition this out, like those match up, right? At the end, we have that. Okay, now check this out. This is really going to be cool. Do you agree that what's in yellow, that right there, do you agree that that's smaller than 1? That's less than 1.
Yes.
No matter what n you give me, that's smaller than 1. Yes? Do you
Yes.
agree that this blue one is smaller than 1?
Yes.
Okay. Do you agree that this green one is smaller than 1?
Yes.
Yes?
Mhm.
Okay. Do you agree that every one of the things in here, whatever they are, that all of those are smaller than 1?
Yep.
Yes.
Yeah. Okay. Do you agree that the first one right here is 1?
Mhm.
Okay.
Yes.
So what you're telling me is this whole expression right here is the number 1 times a number that's smaller than 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 1, all the way till I get to the end. And at the very end, do you agree? Well, that is smaller than 1, isn't it?
Yes.
But would you also agree that it's equal to 1 over n? I mean, it
It
is 1
is.
over n, right?
Yes.
So you have this. You have 1 times a number that's smaller than 1 times a number that's smaller than 1, smaller than 1, smaller than 1, times 1 over n. So can you conclude from that that this whole thing has to be less than 1 over n?
Yes.
Yeah?
Yeah.
Because it's 1 over n times 1 times a bunch of numbers that are smaller than 1. So that those should make this thing smaller, shouldn't it? So this whole thing is less than 1 over n. But would you also agree that this whole thing must be bigger than 0? Yeah?
Mhm.
Because all of these are positive numbers, so it has to be bigger than 0. Now what we can do, if you, I don't know if you've seen this before in Cal 1, but what I've created here is a string of inequalities, and I'm about to apply what's called the Squeeze Theorem. The Squeeze Theorem. The Squeeze Theorem says, if you're trying to figure out what the limit as n goes to infinity of that is, but you know that this whole thing is stuck between two other things, then you can take the limit as n goes to infinity of this one, and the limit as n goes to infinity of this one. And if these two go to the same number, then the middle one has to also go to that number. So if I take the limit as n goes to infinity of 0, well, 0 is 0, so that doesn't change. What's the limit as n goes to infinity of this one?
0.
0. Okay, so look, if this goes to 0 when you take the limit, and this goes to 0 when you take the limit, then where does that have to go?
0.
0. The only place between 0 and 0 is 0. It gets squeezed in between, right? And that's how we conclude that the limit is 0, that it converges. That's a weird one.
Yes, it is.
Say again?
No, yes, it is. It's so it converges.
It converges to 0, yep. All right, it's 2:33. We don't have enough time to start another problem, but I mean to start the next section. So I'll do another problem. What if you have a sub n equals sine of n to the third plus 1 over the 4th root of n? Okay, does this converge or not? If so, to what? All right, so same thing as the previous problem. You cannot get in here and try and do L'Hopital's rule because, well, you don't even have infinity over infinity. But nothing that we have is going to work in terms of like L'Hopital or any other algebra. So we're going to try and do the Squeeze theorem again. So what I'm going to do is I'm showing this to you because, you know, you have to sometimes see this the first time. I would never expect that you just get this on your, you know, just by looking. So now that I'm showing this to you, you'll kind of pick up hopefully on this. So what I know right now is that numerator, definitely because I took pre-cal, I know that no matter what, the sine function is bounded between -1 and 1. No matter what you ever plug into the sine function, right? Sorry, that should be +1 on the right. Yeah, do we agree with that? Okay, that's all I know. So do you see I've set up a string of inequalities? I have something in the middle, I have two things on the outside. I'm going to try and create a squeeze where these two sides squeeze down the middle one. But I need the middle one to look like my original sequence. So what I'm going to do is I'm going to now see that I have this 4th root of n. I'm going to divide by 4th root of n. And I'm going to do that to each one of these. So do we agree that that must be true? If the thing that was in red was true, then if I divide each of these by the 4th root of n, then we should still maintain that string of inequalities because we're doing the same thing to each one. Yes?
Why
Now-
did we pick a 1 and -1?
I didn't pick it. Think about the sine function, right? This right here is the sine function. It's got some weird stuff inside, but no matter what, when you plug something into sine, the answer has to be between -1 and 1. That just goes back to our knowledge of what the sine function does, right? It's
Oh, yeah.
stuck between 1 and -1, always, right?
Mhm.
So I'm using the fact that the sine function is bounded to create this string of inequalities. And now at this point, I can do a limit. I can take the limit as n goes to infinity of this first one and the limit as n goes to infinity of this last one. And I hope that you agree that if n gets really big here, we get -1 over infinity, which heads to 0. And then this one over here on the right, n gets really big, 1 over infinity, that also goes to 0. And because these both go to 0, well, guess what? The one in the middle must also go to 0. So the conclusion is that this thing converges to 0. So that's called the squeeze theorem. That will probably come up in the homework. All right, you got a lot of work to do for this section. And then next class, we start 8.2 series, all right? We start series.
Does it get
As you
better
read
than
down-
this?
What?
Does it get better than this?
Better?
I don't think so.
Better, I mean, I think it does. It gets much more interesting, but I think it gets more difficult from here.
I
No.
think in terms of difficulty. Yes,
sorry?
I'm saying that in terms of difficulty, it will be more hard.
Yeah, I think right now we're like at a 3. With this section, we're like at a 3, and we're probably gonna get to it like an 8 or a 9. But I think the 8 or 9 is gonna come when we get to like 8.3, 8.4.
Okay.
8.2 is probably like a 5. And then we have like 7, 8, 9s in here. The thing that's going to be part of what makes it hard is that it's going to come so fast. The material is going to really, really come at you quickly. I mean, think about the formula sheets, right? We have, how many class meetings do we have? We now have 7 class meetings left, right? 7 class meetings. I still have to make all of this mean something to you, right? And I have to make all of this mean something to you. And that still looks very foreign to you at this point, right? And we only have 7 class meetings for that to happen. All right, so it's going to be the pace of the material also. It is what it is. This class is just crammed with material. So, and it gets harder at the end. So, okay, the exam, right? If you came in late, if you didn't come in late, you're free to go, of course. But if you came in late, I've changed the schedule. I have not changed it officially in Canvas, but this is the new outlook of what we're going to do over the next couple of weeks that we have. We have 1, 2, 3. We have 4 weeks left after today. We have 4 weeks left with the Thanksgiving holiday in there. And so exam 3, I've decided to make it an at-home exam. I will send that exam out at the end of class on Tuesday, and then you'll have until Friday to do it. I'm really concerned about this, okay? Really concerned, because what happens when I give students take-home tests? That's all they do, right? That's all they do. They're just focusing all their time on the take-home test. You can't afford to make that your absolute priority. You have to still be doing your homework and still keeping up with the material that we're doing next week. You have to. You can't just be like, oh, well, I'm just gonna do all tests next week. I'll catch up with the homework, because I guarantee you 8.2 and 8.3, you're not catching up with that material on Sunday night. Like, that's not gonna happen, okay? So that's why I don't like this take-home thing, is because it's really gonna lead people to possibly procrastinate on their homework, and then you won't recover. Like you just won't.
And that
Going
test is
to-
gonna be basically over chapter, was
Okay,
it 7 and 8?
And we're working out 3.5.
I was like, who's that idiot talking? Stop talking. That was me. Okay, 8.2, my series homework assignment took me an hour and a half. The 8.3 took me 2 hours. The 8.4 took me 2 hours. The 8.5 took me an hour and a half. 8.6 took me 2 hours, 15 minutes. 8.7. So all the homework assignments from here on out are pretty long. Like as far as time. Was someone
And
asking?
usually it takes longer to settle in all the problems.
Yeah. Yeah, it takes me that long, but that's, that's me knowing which way to go. So it's,
At least double the time.
So I have a question.
yeah.
You said you'll give us the test after, I think it's like next class?
Next Thursday.
No,
Next
on Tuesday.
Yeah, okay, so next Tuesday. And so we'll have 3 days to complete it. But does that mean that series will also be in that test because we're already
Well,
after
okay.
class?
As far as what's going to be on the test, at minimum 8.1. 8.1 is where I plan on stopping it. However, I might do one thing from 8.2. It just depends on how it goes. I don't know. Right now, it looks like it would just be 8.1 is where we would stop.
Okay, so don't completely erase the possibility of 8.2 not being there.
Yeah, it's just, I would hate to give you something on Tuesday and test you on it on Thursday,
Okay.
I mean, and test you on it immediately, right?
So
Yeah.
chapter 9, as for my understanding, is not included in the syllabus anymore.
It's not, and that's very normal. That's very normal for my Cal 2 classes. I've only reached chapter 9 in my entire career. I've been teaching Cal 2 for like 20 years. In my entire career, I don't think I've reached chapter 9, but maybe 3 times.
We're not complaining.
Yeah. The thing, what I'll do is at the end of the semester, I'll give you links to those videos and I'll be like, hey, for your own benefit, just go watch those. I think I said in the very beginning, chapter 9, the material in there is not, it's kind of like chapter 8, you're going to get your ass kicked. Okay. Like you're going to feel beat up. And so when you get to chapter 9, if someone, just kind of like slaps you on the wrist, you're like, big deal. It's so lower level than chapter 8 is that you can absorb it a lot better. And I think that's really kind of like what Cal 2 does to you, especially chapter 8, is it like takes like what you thought punishment was up to a new level. I don't know if punishment's the word, suffering. Takes your level of suffering. So now like what you're used to now when you get to engineering analysis, like you've experienced suffering. So now you're ready to handle more of it, I guess, right? And it's not so bad because you've been through something like that before.
I've taken engineering analysis and I think this chapter that we're looking, I think it's worse than what we see on EA1.
Yeah, maybe. Yeah, depends on how it's presented, I guess, but chapter 8 is important for a lot of reasons, computer science majors especially, but it's your real first kind of like exposure to logical thinking, where you really have to, like your answers, when you write your answers down, you have to explain your logic, because what's going to happen is when we get through 8.2, 8.3, 8.4, when we get through those 3 sections on a test, on the final, you'll be given a series, and all you'll be asked is, does it converge or diverge? That's all you'll be asked. It'll be a simple question. So like a yes or no. And to do that, you're going to have to figure out, which of these, God dang it, come on. You're gonna have to figure out, see, this is the convergence and divergence tests for series. So these are all the different tests that you could possibly run to figure out the convergence or divergence of a series. And so when I present you with a problem, you have to not only know which one of these you're going to use, but then for each one of these, there's certain things that you have to show. So like if you want to do this comparison test, you first have to, well, and we're getting ahead of ourselves, but you have to understand how to implement the test, like how to execute the test. Like the comparison test, just as an example, what you have to do for the comparison test is I give you a series, which you don't even know what a series is yet. I give you a series, and then you have to look at that series and go, you know what? I have no idea what that does. But it looks a lot like this other series that I do know what it does. And so I'm going to compare the two. So you have to come up with the other series you're going to compare it to. You have to come up with that out of your head, right?
Mhm.
And then you have to actually compare them, and you have to compare them in the manner that this process describes. So, and that's just one of many tests. So I think it's the first real exposure to truly having to understand the direction you're going, explain that in words, like I'm going, you know, by the integral test, right? Here it says integral. By the integral test, you know, here's what I want to show. Okay, here I go. I show it. Oh, therefore my conclusion is that it diverges. And so you have to be able to like write that all out. Yeah, I mean, yeah, okay. You have a lot to do. 8.1, let's get through that. Once you get through that, then we start series next time. All right?
All right.
Have a
All
good
right,
week.
thank you, sir.
Have a good weekend.
Have a great one. Thank you.
Yeah,
Have a good weekend.
You have a good day, Professor.
you too. Any other questions or?
Just a random question.
Yeah,
Would formal logic help with series?
I think so. I mean, not that you need to go and take
I already took
class
formal
or
logic.
do reading.
No,
but
because you
just-
you
yeah.
mentioned computer science, and I was like, oh, I have kind of a degree in that.
Yeah, I mean, no, because I mean, yes, because all these tests are going to be based on
Logic, yeah.
basic logic. Now, you don't need to know like
Understand.
truth tables and stuff like that, but you need to know that, you know, if you're trying to show something, right, then you have to know when you've shown it, right? So there's logic in that. There's, okay, here's what I want to show. Let me try and show it. Okay, I showed it. Now, what conclusion can I draw from that? Because these tests that we run, there's all sorts of different little, like anytime you see these inequalities in here, it's telling you, you know, you have to check, is this true, right? Is it true or not? So anyway, it'll help, definitely. Definitely help. Hey, what's going on?
Thanks. You have a good one.
Hold on just a second, okay? Are we good? Yeah, it'll
Yeah.
help you, definitely.
Okay.
Okay. All right, man. Take care. All right, you there?